Well, I'm here to talk to you about research networks. Most of you folks out there are involved in the commercial internet. Your providers, your equipment manufacturers, your carriers, but you're mostly concerned with commercial traffic because, well, in all honesty, that's where the money is. However, there is another piece of the internet out there that has existed longer than the commercial internet by quite a few years, and that's the research internet. In fact, it used to be the internet, so we're going to talk to you a little bit about that piece of slightly ancient history. I'm going to give you a brief history of research networks, which will unfortunately repeat a few of the things Milo just talked about. Not too many, though. We'll talk about the current research networks, and North American research networks I will emphasize. I'm not going to be dealing with all of the national research networks from all around the country, but just the ones here in North America in the NANOG region. Then what the differences are between the research networks and the commercial internet, and why they exist as sort of separate entities, and where research networks are going down the road. First of all, what is a research network? Research network are also referred to as research and educational network. They're non-commercial networks. They were created for the advancement of knowledge. Therefore, by definition, they are non-commercial. That doesn't mean that the commercial environment doesn't get involved. Many of them are managed by commercial firms. In the case of ESN, it's managed by a university, but some of these are contracted out to the AT&Ts and Sprints and all those folks for operation. But they don't normally carry commercial traffic, or at least not as their primary reason for existence, and they are not out there to make profit, and hopefully not too much of a loss either, and are often taxpayer funded. Hey, how can we take a loss? You guys are all paying for it, right? They're generally used to connect between major research institutions here and overseas, and universities and educational institutions. The purpose of them is, frankly, to avoid use of commercial service providers, to make sure that there's adequate capacity for the science. They generally don't have end users, as we normally use the term. We don't have anybody sitting at a terminal directly attached to any of the research networks. They all attach to organizations, universities of various sorts, laboratories, governmental agencies, but we don't have to worry about grandma sitting at home running Windows 95 unpatched for the last 6 or 7 years. That's not one of the things we deal with, thank goodness. Brief history of research networks. Sorry, but yes, some of this does repeat things you just heard. Useful to remember that it was all a research network originally. It was the ARPANET, it was the MILNet, it was the NSFNet. These were networks funded by typically the US government for the purpose of understanding how networks work. Later, they started to provide support as sort of a side function for various research efforts around the country. And as time went on, that grew. Networking and research actually became a fairly minor function of the whole job. And we grew up becoming the folks who provide network connectivity for science research. It's useful also to remember, as Milo said, that back in the 1980s, the research networks were really multi-protocol networks. IP was not dominant on at least the Department of Energy and NASA networks. I believe there was far more DECnet traffic exchanged at that point than there was IP. Certainly on ESNet there was quite a bit more. IP was just a fairly small percentage of the traffic back then. That was largely because of the folks in high energy physics had massive DECnet deployments in those days, and in fact they didn't go away until nearly the turn of the millennium, when finally the Japanese turned off their last DECnet. The Japanese researchers were very tightly coupled to DECnet and very difficult to talk them into giving it up. I was given the honor of turning off the last DECnet support at ESNet, in fact, because I was their primary DECnet support person. Back by the mid-90s, though, IP was dominant, and once again, thanks to work by folks like Milo, the MILNet, NSFNet, all those folks who turned IP into a standard networking protocol, which basically everybody understood. And the SNAs and OSIs and DECNets all faded into history. Not quite entirely overrun by the wheels of time. Though there are those of us who use this protocol called ISIS, and it still uses an OSPF protocol down there at the bottom of it. And in fact, there's a fair amount of that running around the internet. but it's sort of a special corner case. In the mid-90s, suddenly we had the information superhighway. The internet exploded. We had massive growth, and with it, massive problems. I'm now going to mention some places that will bring back really bad memories for the old-timers. The folks who are not old-timers will have no idea about this. I'm going to mention Downers Grove, Illinois, and both East Orange and West Orange, New Jersey. Those were major interconnect points by some of the commercial providers that were very, very congested. And whenever you got a trouble call, you do a trace route and say, oh crud, it's going through West Orange. And you knew that there was not a thing you could do about it except call the folks at MCI and say, can I get more bandwidth through there one of these days? And they'd say, we're working on it. But that was the sort of the way life was then. Congestion was the norm. It just was growing faster than people could install bandwidth. There were also architectural issues. There tended to be choke points where a lot of the connectivity went through one location. The most famous of those is the Hinsdale fire in Hinsdale, Illinois. That one fiber basically took down the entire internet. It segmented into east and west coast pieces. There was very little that survived. I will mention that both Milo's network at NASA and ESNet did survive because we had a 9.6 kilobit line between Fermilab and a NASA facility in Ohio, and for the life of me I've been trying to remember what that facility was, and none of the people I've asked remember either. Unfortunately, I couldn't ask Milo. I bet he does remember. But that kept ESNet alive, and it kept NASA's Science Internet alive when pretty much the rest of the internet was running around in circles, dropping packets all over the floor. As a result of this, there were massive changes in how things were architected. Particularly, people started looking much more closely at layer one and where the wires and the fibers ran, so that this hopefully will never happen again. I'm not convinced that in time people won't forget about that, and we're going to have Hinsdale too, someplace in the country, but that'll be long after most of us are retired, I'm hoping. Well, university researchers became very discouraged by the performance of the network in those days, and so they decided that they would start establishing their own networks that were using their own bandwidth that they controlled and would not be subject to the congestion caused by commercial growth. And after a while, we had quite a few of these. Here are the major North American research networks of which I am aware. There may be some others out there, but I suspect I got most of the big national networks. I'm not listing regional networks in this. There's, of course, ESNet. There's Internet 2, National Lambda Rail. Those are run by ESNet by the Department of Energy. NLR and Internet 2 are mostly by educational institutions. N-Wave is the NOAA backbone network. Canary is a research network in Canada. NASA still has its research network, and the Department of Defense has DRAN. I know more about ESNet than I do about any of the others since, well, I've worked there for the last 17 years, which gives me a little bit of history on the place, and was involved in ESNet much, much before that as a representative to some ESNet committees from Lawrence Livermore National Laboratory, which is where I was working before ESNet. ESNet is one of the oldest networks that's been continuously operating. It was started back in 1976. That was back before most people had any idea what a network was, before I had any idea what a network was, in all honesty. Originally, it was called the MFE net, and it was created to support global research into fusion energy. Early on, it ran over 56 kilobit per second satellite links to other US facilities, Asian and European facilities. It used its own protocols. They were truly strange protocols that were based on an early DEC network design document. We refer to it internally as DECnet Phase 0. Digital never created a network using those protocols, by the way, and it had all kinds of interesting and strange behaviors, but it did work. In 1986, MFE-net merged with the DECnet-based HEPNet into a single network, and it was renamed ESNet, the Energy Science Network, and started major transition to IP and major transition in technology from T1 days to DS3 days. And yes, I remember very well the fun with that Sprint contract and all the challenges that Milo mentioned. That one took roughly forever. It's amazing how difficult these things were in those days, and frankly, they're not a lot better now. The network supports the United States Department of Energy's Office of Science funded facilities, And that office is the largest funder of basic scientific research in the United States, possibly in the world. So if there's basic science research going on, odds are pretty good that in some manner or another, ESNet is involved in the data of that organization. In addition, we serve NNSA, that's the defense research folks at DOE, the weapons folks who deal with nuclear explosives, and various other federal agencies on a reimbursement basis. In other words, they pay us to carry their traffic. Here's the ESNet backbone, more or less as it is today. This is a few months out of date, but it's pretty close. The heavy blue lines are our science data network. This is a network dedicated expressly to moving science data. It varies in bandwidth depending on location between 20 gigabits per second and 50 gigabits per second. It is used to create dedicated circuits of reserve bandwidth, so scientific researchers can be absolutely certain they will have the bandwidth they need for a given product. The skinny black lines, those are 10 gigabit IP networks. That's our general purpose network. As you notice, they just pretty much run to all the same places. Not quite, but pretty close. And we have therefore a very robust network, and we need it because basically we are not allowed to be down for any length of time, because when we are, data gets lost. And I mean lost forever. And when you got a multi-billion-dollar experiment and some data gets lost forever, people will sit around saying, gee, could the Higgs boson have been someplace in that data that got lost when the network was down? I don't want to be the person who has to deal with that issue. Internet 2, this is really the start of the idea of separate research networks. The educational institutions basically decided they were going to build their own network. They were having congestion problems, and so in 1996, 34 universities got together and announced they were going to create a state-of-the-art backbone over OC48 circuits, which in 1996, OC48 was very much state-of-the-art. The network actually was built in cooperation with ESNet. We had a common layer 1, as we do to this day. It's grown to over 200 member institutions, over multiple 10 gig E circuits. Thank you, DWDM. Provides high reliability with multiple cross points between the northern and southern routes, so that we're very robust against backhoe fade. We may have some links that go down, but the network does not. Primarily, we can connect to regional educational consortia, commonly referred to as gigapops, and they're put together by various universities for the other educational institutions in their area. Their operations vary a great deal, and I'm not going to go into that because I simply don't have the time. There's the Internet 2 backbone map. I believe it is reasonably current. If you think it looks a lot like the ESNet map I showed you a few moments ago, it does. Both networks are built primarily on level 3 fiber, and therefore they tend to follow level 3 fiber paths. So they look very much the same. We do have routers in some places that Internet 2 does it and vice versa, but the footprints are pretty much the same. Canada decided to build its own research network. In fact, they were one of the leaders. They got started back in 1990. Admittedly, it was over 9.6K links, but it was a Canadian research network way back then. In 93, they went to 56K. Now they run over WDM OC192 circuits for the places where it's reasonable to get fiber. Canada's a big country with some very large open spaces, so the entire network is not yet OC192. Network is currently over 19,000 kilometers, connects nearly 200 colleges and universities along with 86 government laboratories, and they average about 7 petabytes a quarter of data. And there's their map, which looks nothing like the ESNet and the Internet 2 maps. National Lambda Rail was founded in 2003 by consortiums of universities and Internet 2, interestingly enough. The initial goal was to create a footprint of 10 gig waves which researchers could basically rent to do network research and to support specific projects. It was not considered to be a high reliability network. It was supposed to be cheap and quickly configured to do specific jobs. However, it's morphed from that into basically a competitor with Internet 2, and in fact there was one time talk of a merger, and there's still a strong feeling of competition, I believe, between Internet 2 and NLR. NLR now provides connectivity at layer 1, which they call WaveNet. That was the original goal. Layer 2, which they call FrameNet, and layer 3, which they call PacketNet. It is operated by 13 member organizations, but does connect over 200 colleges and universities through regional optical networks. There's the National Lambda Rail Network map. Looks quite a bit like the ESNet and Internet 2 maps. Their fiber is mostly from Level 3, but they also receive donations from Wiltel before Level 3 bought them, and from AT&T. So they do have some somewhat different fiber paths. It's very close, however. There's a number of other research networks which provide less general purpose access or are more focused on specific enterprises, and those include DREN, the Defense Department's network, NWAVE, NOAA's research network, and NASA's research and engineering network. All provide networks for research to the sponsoring organizations. They all interconnect with one another, and frankly, all of them are pretty much opaque because they're largely enterprise networks. They don't deal with multiple politically diverse organizations like Internet 2, National Lambda Rail, Canary, and ESNet do. Why are research networks different? Well, the commercial internet mostly deals with email, web access, BitTorrent, things like that. These are things where you don't worry about losing a little bit of data here and there. It'll all get made up after a while, or there'll be a slight glitch in the audio or something like that. But the world is not hinging upon getting every packet through. ESNet and the other research networks deal with large, in many cases multi-terabyte data sets. Those have to be moved around the world, and most commercial networks are not set up to provide that kind of service. The biggest driver is what we refer to as big science, and examples of that include the Large Hadron Collider at CERN. That's currently the biggest user. Supercomputer simulations, which the NSF refers to as the third leg of science. Astrophysics and astronomy. Huge amounts of data collected in really awkward to get to places. Perhaps not as awkward as some of the ones Milo talked about, but still, they're not exactly at the center of the population basis where you've got lots of fiber, or any wire, or any people, or anything. They tend to be in difficult places to get to. Some of these, such as large computer centers, are likely to require terabit per second data rates within the decade. That's a bit of a challenge. And because they're moving large data sets, we're not talking about small flows that can be aggregated. At best, we can parallelize a large transfer into a few separate flows, but we've got to be able to move very large, multi-gigabit per second flows reliably through research networks. They're also used for remote control, real time, basically running experiments so that the experimenters are someplace sometimes far away, and for the area of doing data analysis between runs of a scientific experiment, where you've got a hard deadline to complete your analysis and get the data back so that the next run can be adjusted accordingly. LHC is the big example of big science. It's been running for longer and been moving more data than anybody else. It involves multiple independent experiments, all located at CERN, each generating terabytes of data. We're talking multi-gigabit per second data flows that may run for many hours. Drop packets are devastating. I mean, you may have rapid recovery, but it's not that rapid. And when you're talking about multi-gigabit flows, it just doesn't work well to have to do that very often. So we can't afford to have dropped packets. Tuning of both the full network and end systems is absolutely critical. Most people don't tune their systems to run in this type of environment. We spend a lot of time and effort on dealing with the issues of trying to get systems tuned for this. Firewalls are particularly a joy to deal with, by the way. The system also includes specialized caching and storage systems to handle the large volumes of data that are flowing in so quickly. And those systems are scattered around the world. The major ones in the US I'll be getting to shortly. We support this by the use of on-demand circuits. People say, we're going to be moving data at 5 gigabits per second for the next 2 weeks. We need a reserved 5 gigabit path between CERN and Fermilab, for example, for that period of time. The data primarily flows under the Atlantic to Fermi, Brookhaven National Laboratory, and Triumph in Canada, distributed from CERN to those laboratories, and then stored and distributed on demand to research and educational institutions around the globe, primarily, of course, from those locations to the US. Theoretically, it should be moved from Tier 0 to Tier 1 to Tier 2, but in fact, nobody can maintain the full data sets. So if you need data from some other place, you may be hauling it in from Europe, you may be hauling it directly from CERN. That was not the way things were planned, it's just the way things worked out, and the people who behind the LHC project have finally given up the ghost and admitted there's no way it can be made a structured, hard-tiered system and actually work. How much data are we talking about? Well, the maximum data transferred so far to Fermilab from the CMS experiment is 74 terabytes in one day. That's a lot of data to be going between just two endpoints. And the average daily data, 30 terabytes per day. The ATLAS experiment has hit a maximum of 93 terabytes and averages 49 terabytes per day. Once again, large volumes of data that need to be moved over paths with a lot of latency. The other area is remote control. It generally requires minimal delay. You've got to be able to interact rapidly. Can't do much about the speed of light, but in other respects, you work to try to make things run in as fast a method as possible. Use expedited forwarding. Places where this is used are health checks for automated protein crystallography, and for the control of fusion experiments from General Atomics in San Diego to Princeton Plasma Physics Lab in Princeton, New Jersey. Not exactly next door neighbors. To make all this work, we use a circuit reservation system that was jointly developed between ESNet, Internet 2, and ISI East to be able to create and destroy rapidly L2 and L3 VPNs between end systems. Currently, over half the traffic on ESNet travels over these dedicated circuits between well-defined research sites. There's the regular map showing the traffic increase. In December, we moved 8.3 petabytes of data. November was a big spike, but it's slightly bogus. The supercomputing conference goes on in November, and there's lots of demonstrations and tests and so on that run in conjunction with supercomputing, which artificially spikes that. So that huge November number of 10.6 petabytes is an anomaly. Nonetheless, there is a lot of data being moved by ESNet on this. Need a lot of reliability. Our goal is absolutely 5 nines. In fact, last year we did 4 nines and an 8, so we came very close this year. I'm hopeful that ESNet will make it to the 5 nines. And that's critical because CERN has limited ability to buffer data. The data coming out of the experiments must be moved to the caching sites around the world or it is lost. Once again, that's not acceptable. We use PerfSonar as the key tool, and I have a link up there to get to the PerfSonar website. Provides a network of systems for doing ongoing or specific tests. It allows us to monitor network health and spot problems early on. It's widely deployed through ESNet, Internet 2, and in Europe, not just to the network backbone sites, but also to end sites. And it has administrative access controls so that we can make sure that the tests that are run are not intrusive on production data transfers. As you can imagine, since these things are capable of testing at a full 10 gigabits per second, we could interfere with traffic on a 10 gigabit link rather easily. So we make sure that that does not happen and that does not step on reserved bandwidth. Where are we going in research networks? Well, more bandwidth, surprise, surprise. Most research networks are currently trying very hard to move to 100 gigabit per second waves and replace the old, slow, painful 10 gigabit per second waves, which sounds really funny when you remember the days of 9.6 kilobit networking. We're looking at more efficient use of the spectrum, getting more data into a single fiber. That's a critical area because fibers are expensive. Electronics are relatively cheap. For those of you who bought a WDM switch lately, they're not real cheap, but compared to running a fiber across the country, it's cheap. So that's one of our goals. The other is to enhance middleware to make more efficient use of our available bandwidth. We're making improvements to OSCARs to better schedule bandwidth, including automated L3 VPN creation when we see large flows that are ongoing between locations, move them basically to the Science Data Network automatically and transparently. Our other major effort is to tune end systems. And for those of you interested in how to make your system perform better on its network connectivity, we provide a website, fasterdata.es.net, that provides a great deal of helpful information on how to tune systems. I will point out that yes, some of the information there is pointed at people who are moving multi-gigabits, but a great deal is perfectly applicable to any system that wants to move data rapidly across the network. And right now, this is the 100 gigabit network that ESNet is working on building. It should be this year, connecting the East Coast to the West Coast and down to Oak Ridge, being funded by the federal government out of stimulus money, the Advanced Networking Initiative. So the research and commercial networks have a lot in common, but their basic goals and needs have diverged over the years such that they are really separate internets that just talk a lot to one another. They still have a great deal in common. We're still running IP, BGP, OSPF, ISIS. Those things are all common, but some of the engineering details are quite a bit different because of the specific needs of the two networks. Both of us obviously need more bandwidth, that's a given, but the way we implement it may in fact be quite a bit different. Techniques and tools that are developed by the research community, though, may be of use to the commercial community. Things like perf sonar and faster data, for example, both could quite possibly be very useful to commercial providers, and they're free. Can't argue with the price. And I believe that more awareness of what the research networks are doing could be very beneficial to those commercial folks out there as well. That's one of the reasons I'm up here. And just finally, on a side note, this is my last week at ESNet, and I want to thank the folks at NANOG, the folks at Merit, all the folks who made all this possible. The value that I have received from NANOG and ESNet has received from NANOG is tremendous, and without NANOG, this would be a very different internet that we have today. So thanks to everyone. I'm going to miss you out there, and as I go sailing off to a new sunrise in Hawaii this next weekend.
Well, thank you, Kevin. Kevin's been a great member of the PC, helped us put together all of these talks. I guess you're getting some questions here. We can run into the break for a little bit.
Just remember, you're cutting into the break here, so try to keep it fairly brief or the natives will revolt. The front mic, Michael.
Michael Sinatra, ESNet. I almost said UC Berkeley. ESNet. First of all, it takes two people to replace Kevin. As one of the two people replacing him, I want to thank him for all he's done for NANOG over the years, and for ESNet, and for me personally. Yeah. I recently ran into a video on YouTube of a gentleman who claims that Internet 2 is a giant conspiracy by the government to retake over the Internet because it has an AUP, and he uses the Internet 2 logo. So clearly he has enough basis in reality that he must have read something about Internet 2. I was wondering if you could respond to that. Are research networks really trying to take over the world? And if so, what's it going to look like?
Oh my gosh, somebody's discovered our secret plan. We're doomed. No, I don't think research networks are going to take over the network. For one thing, we don't have nearly enough money. And by the way, I believe that he has, for probably the third, fourth, or fifth time, been banned from the NANOG mailer. I'm sure he will return again someday when he gets a new mail account that we don't recognize until we figure out who it is. The back mic, Randy.
Randy Bush, IIJ. Kevin, you've given far more than you've taken. Thank you. I would have expected, looking back over 10 years of going to research network meetings, I would have expected to hear more about optical switching. Well, what happened to it? Why?
We have a great deal of optical switching. We just don't have optical routing. Every ROADM out there is doing optical switching at some point. But I'm not really sure. There was an interesting project to build an optical router at the University of Southern California, which I followed for a while, and it sort of, I haven't heard much from it for the past couple of years. It's really, really difficult to move data without getting electronics involved at some point today. Our photonics just, I don't believe, is developed anywhere near that point. I can assure you that research is still ongoing into that, but not by those in the research network community, but by individual researchers at universities and other research sites. And whether it'll ever come to fruition, I have no idea. I kind of suspect that it will. I don't think it's going to be real soon. Don't see anybody else, so hey, run for the break. The goodies are out there, I hope.
Yeah, let's come back at 11:30. Thank you all.